Okay, so today we are going to look at the rules for differentiation, and I'm hoping that you read through this section of the book that I asked you to read through yesterday. So we're just going to clarify it a little bit today in case the notation confuses you at all. So anytime we're taking the derivative of a constant, it's just going to be 0. Remember that this notation, d dx, just means the derivative of, and c just stands for a constant. So the derivative of a constant is just equal to 0. So if we're asked to differentiate the function f of x equals 5, we are looking for f prime of x, its derivative, and since 5 is a constant, its derivative is just 0. So we don't have to go through that whole long limit notation, taking the limit as h approaches 0 of f of a plus h minus f of a over h, or the limit as x approaches a of f of x minus f of a over x minus a. We can just say we know these things about derivatives. This is true. We also have a power rule for derivatives. So basically, what our power rule says is when we want to take the derivative of something raised to a power, we're going to take that power and just pull it down in front of our thing and multiply by it and subtract 1 from the power. So if we want to find the derivative of the function f of x equals x to the 22nd power, its derivative, f prime of x, we're going to bring that power down front times our x thing to 1 minus what our power was. So 22 minus 1 would be 21. So we have f prime of x equals 22 times x to the 21st power. That's our derivative. We have a constant multiple rule. So our constant multiple rule says that we can bring that constant out front and ignore it and just take the derivative of the other part of our function that we have that we do know how to take the derivative of. So if we have f of x equals 4x squared that we want to differentiate, we could say that its derivative, f prime of x, well, that 4 we'll just ignore for now. X squared we'll just use the power rule on. So we'd bring our 2 up front. We have our x. 2 minus 1 would be 1. So this becomes 4 times 2x to the first, or 8x to the first, or just 8x for our derivative. We have a sum rule. So if we're taking the derivative of the sum of two functions, that's the same thing as the derivative of the first function plus the derivative of the second function. So if we have f of x equals x to the 7th plus x to the 6th that we want to differentiate, we can say that f prime of x, its derivative, is just going to be using the power rule 2 times here. So we'd have 7x to the 6th plus 6x to the 5th. Our difference rule works almost exactly the same way, only we have a difference. So the derivative of a difference of functions is the derivative of the first function minus the derivative of the second function. So if we have f of x equals x to the 7th minus x to the 6th, when we differentiate f prime of x, we'll have 7x to the 6th minus 6x to the 5th. So this allows us to differentiate functions in a much easier way than working with those limit definitions of how to find the derivative. So if we want to differentiate the function f of x equals 2x cubed minus 3x squared minus 4x, we can say that f prime of x is going to be that constant 2, and then we'll use our power rule on the x cubed. So we bring our 3 down front. We have our x. 3 minus 1 is 2, so our new power is 2. Minus 3 times, we use our power rule on the x squared part. So we bring our 2 down front of our x. 2 minus 1 would be 1 is our new power. And then minus 4 times, we can use our power rule on our x here. So we'd have a 1 is what our power really is, and then x to the 0 power. So this is really just 6x squared minus 6x minus 4. Sorry. If we have fractions in our powers, it still works the exact same way when we do our power rule with derivatives. So if we want to differentiate the function f of x equals x to the 5/3 plus x to the 2/3, don't let those fractional powers throw you off. We still do the exact same thing. So we would say that f prime of x is going to be, with x to the 5/3, we'll bring that 5/3 power up front and multiply it. So we have 5/3 times x to the 5/3 minus 1 would be like 5/3 minus 3/3, or 2/3 for a new power. Plus x to the 2/3, we'll bring that 2/3 power up front and multiply it. So 2/3 times x to the, 2/3 minus 1 would be 2/3 minus 3/3, or negative 1/3. And we could turn that into a fractional looking thing where we take our exponent and move it down to the denominator to make it positive. But then we have a fractional exponent in the denominator, and so we have to rationalize it. So you can just leave any negative exponents that you get just as they are. You don't have to worry about moving them around within the fraction.